Hi, my name's Andrew McLaren, and I'm going to help you understand Newton's third law today by looking at two boxes that are stacked on top of each other and the forces that are involved. Sometimes people can get a little bit confused with this because there's just no numbers involved, but this I'm going to try and emphasize actually giving values in newtons using some relatively simple numbers, but things that actually relate so you can actually see the equal and opposite forces in this problem. We're going to do this first with the boxes just stacked on top of each other, and then one where they're being pushed and there's some friction involved. So to get us started, if we're talking about object A and its force diagram, it's going to be a little bit tricky because there's force of gravity down for A, and it weighs 2 kilograms. So if we just do the mass times acceleration of gravity on that, then you're going to be getting 2 times, I'm just going to keep it very simple, we're going to use the negative 10 meters per second squared. So this is about down at negative 20 newtons there. There's also going to be a force normal of A where there's some force pushing up on this. And you might think that this is equal and opposite to that other force involved, but there's a problem. So if we look at object A and we just draw a circle around it, not only is there the gravity down and the floor pushing up on it, but there's another force that's involved pushing down on A, and that's going to be the force of B on A, which is kind of hard to solve by just starting with A. So we're going to pause on getting those numbers, and we'll come back to that. But it's pretty easy to do this for object B. So if we talk about object B, it's going to be just really like the force of gravity down and the force up on it, which you might call force normal, but it's the force of A pushing up on B. So the ground isn't in contact with B, so it's not got that force normal that you would normally use in these types of problems. So if we look at object B here, it is going to have a slightly smaller force of gravity because it's a smaller object. So I'm going to try and keep that to scale, or at least approximately to scale. So this is the force of gravity on B, which its mass times the acceleration of gravity would be 1, and I forgot to put my units there, so 1 kilogram times the negative 10 meters per second squared. In other words, this should be negative 10 newtons. So for object B, the amount of force that it's getting pushed up is preventing it from falling, so like those forces cancel out. So the force of A on B is equal and opposite to that force of gravity. So it's going to be a positive 10 newtons. In other words, the sum of forces in the y direction for B is equal to 0. So the force of A on B and the force of gravity on B, these cancel out. And by doing this, we're able to see the how much the gravity is pushing down, causing that to push up, which is equal and opposite to how much B is pushing down on A. So the force of B on A now is going down at the negative 10 newtons. So this is that Newton's third law that's involved. Similarly to what we just talked about with the other one, the sum of forces in the y direction of object A is going to be these three forces that are canceling out. You've got that force of gravity of A, you've got that force of B on A, and you've got that force normal, which we normally just write as F of n, or sometimes n. I prefer to use forces starting with F always though. So then we've got that force normal here that's involved. You can see that has to cancel out these two that are going down by having it go up with the same magnitude, canceling that out. So this needs to be a positive 30 newtons. And so you could plug in the numbers here and see this is like a positive 30 newtons, a negative 20 newtons, and a negative 10 newtons. So those two together cancels out with that because this object is not accelerating upward or downward. Remember, the sum of forces can be related to the mass times the actual experienced acceleration. And because this object is not like accelerating upward or downward, because that value is 0, then the sum of forces should also be 0 in this type of problem. So we have this when there's no friction involved. It's pretty simple. And you can see what I've got labeled in that kind of lighter purple color. It's kind of like a pink color. That's our equal and opposite force. Now you could have a similar type of setup here. We're going to keep the same masses, but now we're going to have a force that's applied sideways. And if there's no friction between these two boxes, object A and B, they can't move together. I'm also going to, just because it's somewhat useful for the big picture on this, I'm going to consider these two objects moving together before we actually do that. So if we have the force diagram of A plus B, you can talk about them as like one larger object, and the equal and opposite forces, they kind of cancel out. So there's this force diagram that we can do for A plus B together. And in that context here, the force of gravity down of A plus B, because we have the 3 kilograms now, it's the 2 kilograms plus the 1 kilogram. You're going to have like 3 kilograms times the -10 meters per second squared, aka -30 newtons, pulling it down. And then that surface is still pushing up, equal and opposite, with a positive 30 newtons. So in a sense, this internal force can be thought of as like the amount of gravity that's being applied from object B downward on A. And so you can continue to think like that and actually add those two gravities together when you put it into this larger system. These internal forces, they kind of cancel out. Like if I'm looking at a person and how much force is acting on them as they like are being pushed by something, you're not going to look at like the internal forces of what's going on with them pushing the food in their stomach and their food pushing back on them. So the same sort of idea here is that you don't need to worry about internal forces when you look at this larger system. So we'll be doing like all of those types of steps, but now we're going to say that there is some force that's being applied. Maybe there's some tension on some rope that's attached to object A. And so this is going to be at, let's say, 2 newtons. And we're going to have a coefficient of friction that's static of 0.7. And then if we look at that, actually, you know what, I'm going to change this slightly. Let's go with 3 newtons. I think that'll work out better with the numbers that we were working with. If we look at this, the force of static friction is going to be something that scales up as you apply a force until it gets to the point where the static friction maxes out, and then you get this kinetic friction. So when you use this 0.7 equation, that's going to be relating like how much it goes upward up to a maximum, and then you've got this like force kinetic, and then this is that force static. So this is like the maximum value with that 0.7 number. We probably, in the context of this problem, are not going to get all the way up to that. We're going to be somewhere a little bit less. Like, think about this. If you are pushing an object, you have the friction canceling out until it's not. So if you were pushing with like 10 newtons and there's like -30 newtons possible friction preventing you from moving, it's not moving backwards. It's just scaling up as much as necessary to cancel out how hard you're pushing. So let's look at object A and object B. and we'll also do the a plus b. But I think it's easier to start with b, so we'll go ahead and do that in a similar context to what we were doing last time. So we've got our force of gravity down here. You've got a force up, force of A on B, and I'm just going to use the values that we talked about earlier because it's the same mass. So we've got B's being pulled down by negative 10 newtons, and we've got this positive 10 newtons. And then if there was no friction, B would just stay still. So friction has to explain it moving with the rope. So for it, there's going to be a force of friction that needs to pull it this way. So we've got that force of friction. For B, it needs to go that way. We'll solve its actual magnitude in a little bit. This is not necessarily to scale. I might need to actually make this a little bit smaller, but we'll get there. So in a similar sense, A has some forces that are acting on it. So it's got its force gravity downward, which is bigger than what we just drew. So just kind of make that to scale, we'll make that quite a bit bigger. And you've got the force normal kind of going up. And we're getting a force downward on this, the force B on A, kind of pulling that down. So if we've got a negative 20 newtons here, like we did last time, and we're seeing that this is a negative 10 newtons there, then we have to have a force that's going up on this of plus 30 newtons. There's going to be a force that's being applied by this tension going sideways. And then there's going to be some friction actually going equal and opposite in the other direction. But I know that it's going to be smaller than the force of tension because this thing should be accelerating sideways. We know that this force friction is probably smaller than the force of tension, but it's hard to say exactly how big it is at this point. So you actually need to consider objects A and B together to figure out what's going on individually. So if you look at the two together, you've got this much larger force of gravity downward. You got force of gravity of negative 30 newtons, like what we saw earlier here. And you got force normal of positive 30 newtons. The internal force, that friction, if you think about A and B together, there's that internal force we don't need to worry about. We're just worried about what's acting on it, pulling it sideways. So it's got that force of tension pulling this system sideways at about 3 newtons. So it's actually quite a bit smaller than these other forces that are involved. We're going to make it like pretty small in our diagram. It's not perfectly to scale. It's like 1/10 of the value of what we were talking about earlier. So we've got the 3 newtons there, and it's going to cause some acceleration for this larger system. So the sum of forces of A plus B is equal to its mass times the acceleration that it's experiencing. Because we have 3 kilograms total between those two boxes, and the sum of forces in the x direction here is just one force. It's just the force of the tension of this rope that we labeled in this light blue. We're able to take that value, that 3 newtons, and find the acceleration of this whole system. And as you can see, the numbers that we've worked with here get you an acceleration of 1 meter per second squared. I'm going to notate going to the left as being positive here. So that's just going to be important to keep track of that sign being positive for when we look at the individual forces later on. You can have that be the case. You just got to be smart and think like, okay, this is like now my positive direction, my vector system, and my negative direction, my vector system. So we've got an acceleration that is related to the motion, and that is going to help us find out what's going on with the sign and magnitude of this force friction. So if we look at the sum of forces on object A here, it's got that force tension and it's got that force friction, which is going to be related to its mass times the acceleration that we're experiencing. Because this is all moving as one system, the acceleration of object A is the same as the whole system. So object A is accelerating at +1 meters per second squared, and A, I believe we said was, yeah, it was 2 kilograms. And if we have 2 kilograms times 1 meter per second squared, that means that the sum of forces is going to be +2 newtons. In addition to that, we have this force of tension, which was 3 newtons. And then we have this force friction, which we can now solve for. So we've got 2 newtons total going to the left being a positive direction. We have the force of tension going to the left, having that being a positive direction. And we can then solve for the force of the friction. So this friction right here, now it looks like is a -1 newtons. And that lets us talk about what's going on for object B. So if we look at object B, its sum of forces for B in the x direction is just that force of friction. And because we were saying that's the positive direction going to this left side, we're going to now need to notate that as being a +1 newtons, which is equal to object B, its mass times its acceleration. So we can just kind of confirm, because we have 1 kilogram mass for this object, and it is 1 meter per second squared, the acceleration in that direction, it does appear to work out and give us the same 1 Newton value. So you could solve for the acceleration and see that object B is able to accelerate sideways with this value. There is also this coefficient of friction issue that we're just going to highlight for a second. This coefficient of static friction is going to be the force friction max over that force normal. And in the context of B, it's got 10 newtons that are pushing up from object A on B. And so we've got like our 10 newtons here. And on top of that, we've got that maximum friction, which we're saying is 1 Newton. So it's well within the accepted range, because what we are seeing as our maximum value is much, much larger than what we are actually experiencing. So if we were to look at the 0.7 right here, and if we had our 10 newtons that's like between B and A, then it could be up to like 7 newtons, this force friction. So if we were to pull harder, this object B is still going to be sliding along with A, but up to a certain point. Like we'd have to be pulling quite a bit harder to get to slide off. So that's the main idea with these types of problems. You've got these canceling out forces. Force friction should be related to like how hard two objects are pushing on each other. It's not really related to the ground in this context, because in this context we only gave a coefficient of static friction between the two. In other words, they're sliding on a frictionless surface, but there's friction between A and B here. And it's you're able to see what's going on with this equal and opposite friction between A and B, as well as this equal and opposite force of contact, like kind of like a normal force between A and B directly. So yeah, let me know if you've got any more questions. It can be a little bit confusing. So if I need to clarify anything, just put a comment down and I'll see what I can clarify.